All right, so in this last section, we're going to be talking about geometric and Poisson distributions. We're not going to talk about this in great depth. In fact, we're going to do very little with it, but I do want to cover it just for some extra practice. So the first one we're going to talk about is the geometric distribution. So before we get into the definition, a geometric distribution is used whenever we repeat a trial until we get a success. So we're still talking about binomial distributions, but we're talking about when we repeat it until we get to the very first success, and then we're going to stop. Okay, so an example of that is, I don't know, maybe I'm trying to make a sale call, and I'm going to make phone calls until I am successful, and then whenever I'm successful, I can go home for the day. So that would be an example of a time where I would be able to use a geometric distribution. Okay, so let's go ahead and talk about the definition first. The definition says that a geometric distribution is a discrete probability distribution of random variable x that satisfies these four conditions. A trial is repeated until a success occurs. The repeated trials are independent of each other. The probability of success, p, is the same for each trial. And the random variable x represents the number of trials in which the first success occurs. Okay, so the only difference between the definition here and the definition of a binomial distribution is that a binomial distribution is instead says that it's the number of successes, that we know that what the number of the successes is, where this one is we keep trying until we get a success. Okay, and so we can simplify. We can actually simplify the binomial distribution. So remember, the binomial distribution is this: p of x equals ncx times p raised to the x power times q raised to the n minus x power. Okay, so if we're looking at exactly one success. Okay, so we're looking at exactly one success. We can actually simplify this. So this would be n C1 times p raised to the first power, q raised to the n minus 1, which we end up actually getting very similar to this. So NC1 is actually going to end up being 1. Okay, so we do end up with the same formula if we plugged in one success. All right, anyways, so we have this equation. Let's go ahead and perform an example. So it says, example 1, a study found that the smartphones made by a certain manufacturer has about a 14% failure rate. 6 smartphones made by this manufacturer are selected at random. We want to find the probability that the 6th smartphone is the first one to have a failure. Okay, so we need to do a little bit of finding. So we need to know what P is, Q is, and we need to know what X is. So P is the probability of success. So in this case, it's actually the probability that a phone fails. And I know that's really confusing, but the success here is a failure of a phone. So 0.14. Q is about 0.86. And then X is the 6th phone. So we're going to say X is equal to 6. Okay, and then we can simply plug this in. So P of 6 is equal to 0.14 times 0.86 to the x minus 1, which would be to the 5th power. I'm going to leave this to you to do in the calculator, but you get about 0.06, or about 6% chance. And so I do want to interpret this. Okay, so interpretation. Okay, so what I would say is that there is a 6% chance that the failure will occur on the 6th phone. Or I guess I should say the first failure will occur on the 6th phone. Okay, so again, geometric distribution is looking for, we're repeating the trial until we have our first success. This could be on the first success could be on the first one. It could be on the 1,000th phone. Okay, but we're looking at the probability of success for that happening. All right. So the definition of the next thing we're going to talk about is a Poisson distribution. So the Poisson distribution is a discrete probability distribution of the random variable x that satisfies these conditions. Okay. So again, this one's actually very different from what we did earlier. So the experiment consists of counting the number of times x an event occurs in a given interval. The interval can be an interval of time, area, or volume. Then it says the probability of the event occurring is the same for each interval, and the number of occurrences in one interval is independent from the occurrences in the other intervals. Okay, so the biggest difference is this. Basically, we're given, we can find the average here first, and then we can compute what the values are. Okay, and it's given to you with this really funky equation here. So it says P of x is equal to the mean raised to the x power times e to the negative e to the negative mu divided by x factorial. Now, e is an actual number, and I'll show it to you on the calculator, but e is a number on the calculator, so it's nothing that you actually have to solve for. All right, so let's do an example. So it says the mean number of accidents per month in a certain intersection is 3. What is the probability that in any given month 4 accidents will occur? Okay, so again, we only need 2 things here. We need to know what x is, we need to know what mu is, and we need to know what x is. So we know what mu is. Mu is 3, and we're looking for the probability that in some month that 4 accidents will occur. Okay, so to solve this, I'm simply going to say the probability of 4 accidents is equal to 3 raised to the 4th power times e raised to the negative 3rd power all over 4 factorial. And again, I'm not going to work this out with you, but I'm going to give you the solution. You get approximately 0.168. So there's about a 16.8% chance that at that intersection there will be 4 accidents in a given month. Okay, and that would actually be the interpretation. And I would say the probability of 4 accidents occurring at that intersection in any given month is about 16.8%.